To really understand how your car works, you have to stop thinking of it as a mechanical machine and start thinking of it as a chemical processor. The engine control unit, or ECU, is the head chef, and its recipe for power is extremely strict. The most critical ingredient in this recipe is air, and the mass airflow sensor is the scale that weighs this ingredient. You might wonder, why do we need to weigh the air? Why not just measure how much space it takes up? This is the fundamental concept of engine management. Air is compressible. Its density changes drastically depending on the environment. If you drive your car in Miami at sea level, the air is thick and heavy. If you drive that same car to the top of Pikes Peak in Colorado, the air is thin and light. A cylinder full of air in Miami contains way more oxygen molecules than a cylinder full of air in Colorado, even though the volume is exactly the same. If the computer injected the same amount of fuel in both places, the Miami car would run lean and hot, and the Colorado car would run rich and boggy. The mass airflow sensor solves this by measuring the actual mass of the air entering the intake. This is usually done using a hot wire element. Inside the sensor, a thin wire is electrically heated to a constant temperature above the ambient air. As airflow passes over the wire, it carries heat away. The more air molecules that hit the wire, the more current the sensor needs to send to the wire to maintain its temperature. This electrical current is the magic signal. The sensor converts this current into a voltage or a frequency that the ECU can understand. Now let us look at how this controls fuel injection. The fuel injectors are basically just electric valves. They are either open or closed. The computer controls how much fuel enters the engine by pulsing the injector open for a very specific amount of time measured in milliseconds. This is called the pulse width. When the mass airflow sensor sends a signal saying, "Hey, we have 10 grams of air per second coming in right now," the computer looks at a complex spreadsheet in its memory called a fuel map. It finds the cell that corresponds to that airflow and engine speed, and it sees a value that tells it exactly how long to open the injector to achieve the perfect mixture. This perfect mixture is called stoichiometry, which is roughly 14.7 parts air to 1 part fuel for gasoline. When this ratio is hit, the fuel burns completely, giving you maximum power and minimum emissions. This process is happening hundreds of times every second. It is a continuous loop. You step on the gas, the throttle opens, air rushes in, the mass airflow sensor sees the air mass increase, it signals the computer, and the computer instantly increases the injector pulse width to match the fuel to the new air. This is what we call open loop operation during sudden acceleration. The computer trusts the mass airflow sensor implicitly to give the right amount of fuel instantly. However, when you are cruising on the highway, the system goes into closed loop. Here, the computer uses the mass airflow sensor as the primary input, but it also checks its work using the oxygen sensors in the exhaust. If the oxygen sensor says, "Wait a minute, we are running a bit rich," the computer will tweak the injector pulse width slightly, shortening it to spray less fuel. These adjustments are called fuel trims. The short-term fuel trim bounces around constantly, reacting to second-by-second changes. If the mass airflow sensor is slightly dirty and under-reporting airflow, the short-term fuel trim will go positive, adding fuel to compensate. If this trend continues, the computer learns this and moves it to the long-term fuel trim. This is how the computer adapts to a wearing engine or a dirty sensor. But the mass airflow sensor's job does not stop at fuel. It is also critical for ignition timing. The computer needs to know the engine load to decide when to fire the spark plug. Engine load is basically a calculation of how much air is filling the cylinders compared to the maximum possible air they could hold. If the mass airflow sensor reports a high air mass, the computer knows the cylinders are packed full and the pressure is high. In this situation, it will retard or delay the spark timing to prevent engine knock or detonation. If the sensor reports low air mass, like at cruising speed, the computer advances the timing to get better fuel economy. So if your mass airflow sensor fails, it's not just fueling that suffers. Your timing gets pulled back to a safe, inefficient baseline, killing your power and fuel economy. This single sensor is the cornerstone of the entire engine management strategy. It is the primary data point for almost every decision the computer makes regarding combustion. That is why when it fails, the car usually goes into a limp mode, running off estimated data from the throttle position and engine speed, which is never as accurate or efficient as the real-time data from a working mass airflow sensor. Understanding this relationship between air mass, injector pulse width, and timing helps you appreciate why keeping this sensor clean and functioning is vital for the health of your vehicle.